To your kind introduction, I would like to thank NHR to invite me to this plenary talk. According to the WHO IACR 2014 World Cancer Report showing that liver cancer is the second most common cause of cancer deaths in 2012. So my first part will be the prevention of liver cancer, a study from children to adults. As we understand that there are three strategies of cancer prevention. The first one is cancer control. The first one is cancer prevention, and the second one is the screening and early detection. And the third one is cancer therapy. And among these three strategies, cancer prevention is the most cost-effective way to control cancer. I would like to use liver cancer prevention as an example to demonstrate the three levels of cancer prevention. The first level is primary prevention, which targets the general population using hepatitis B immunization for healthy infants to prevent hepatitis B virus infection and liver cancer. It is with high effect and very low cost, and with time required just very brief and have minimal adverse reaction. In contrast, the secondary prevention uses antiviral therapy to prevent those already have chronic hepatitis B virus infection to develop liver cancer. And the tertiary prevention of the liver cancer using, again, the antiviral therapy to prevent recurrence of those already have liver cancer. Those two have less cost effectiveness than the primary prevention. Since Taiwan launched the world's first universal hepatitis B immunization program, so we have the opportunity to study the effect of universal hepatitis B immunization. And we found that from our 6 serial epidemiologic study at Taipei City, we conducted it every 5 years. And we are very fortunate to have the first study, baseline study, just prior to the immunization program. And we found that children above 2 years old, the surface antigen positive rate are shown in this figure, around 10%, very high. And it declines 5 years later in the red line, and 10 years later in this green line, 15 years later in purple line, 20 years later in this light blue line, and 25 years later in this orange line, showing that those vaccinated birth cohort, the surface antigen positive rate already declined to 0.5 to 10%. So more than 90% reduction of the surface antigen positive rate. This is the chronicity rate, so very successful. But those unvaccinated birth cohorts still have very high surface antigen positive rate. So we can say that primary prevention by universal hepatitis B immunization is the most effective way to control, to prevent liver HBV infection. So we then ask, can this immunization program reduce hepatitis B related liver cancer? Since we are working for children's hepatocellular carcinoma, HCC, so we have the opportunity to study whether children's hepatocellular carcinoma is similar to that in adults. And we found that 90 to 100% of the children of hepatocellular carcinoma are surface antigen positive, suggesting a very close relationship of HBV infection with this childhood hepatocellular carcinoma. In addition, we investigate hepatitis B genome integration into children's host genome in the liver cancer tissues, and we found positive findings. And also, we study their mothers, because adult is more difficult to study mothers, so our children, we are easier to get the maternal serum. So we found that 94% of our HCC children, maternal surface antigen are positive, suggesting a very important mother-to-infant transmission in these hepatocellular carcinoma children. In contrast, in our chronic hepatitis B virus carrier children, only 50% of them mothers are surface antigen positive. And we also found that their liver cancer patients, these children, 86% already have E antigen negative, and the cirrhosis of liver develop very, very fast in those children, very early already. 81% have liver cirrhosis, and which is very similar to what we found in adults. So we study the incidence of hepatocellular carcinoma, the change in the vaccinated cohort. And we found that children and adolescents 6 to 19 years old, their hepatocellular carcinoma incidence is reduced. Here we can see those unvaccinated birth cohort. If we consider the rate ratio of developing hepatocellular carcinoma as 1, then the rate ratio of developing hepatocellular carcinoma in the vaccinated birth cohort reduced to 0.3 to 0.32, suggesting a 68 to 70% reduction of hepatocellular carcinoma incidence. So very successful. So we can say that after the vaccination program, the vaccinated birth cohort, the acute fulminant hepatitis B is reduced. Chronic hepatitis reduced around 90%. And hepatocellular carcinoma incidence reduced around 70%. Here we can see that hepatocellular carcinoma, according to this study, the data is from the selected representatives registry from the 5 continents, showing that hepatocellular carcinoma incidence increased with age in both males and females. So we ask whether, because the incidence of liver cancer is much higher in adults than that in children, and also after infantile immunization, if they grow to adult, they may lose their antibody. So the antibody titer is waning with time after infantile hepatitis B immunization. So we then ask, can infantile hepatitis B immunization prevent hepatocellular carcinoma in both children and adults? So we collect the data of HCC patients at 6 to 27 years old, diagnosed between July 1983 to June 2012. And we use these 2 national registry systems. The first one, National Cancer Registry System of the Ministry of Health and Welfare. The second, we established a new registry system, the Taiwan Hepatoma Study. The members are from all the major hospitals from Taiwan. And we found that those 20 to 27 years old, the young adult, the red bar shows the unvaccinated birth cohort, their HCC incidence, and the blue color shows the vaccinated birth cohort. So we study the vaccinated to unvaccinated rate ratio of hepatocellular carcinoma, and the rate ratio is 0.35, suggesting a significant reduction of hepatocellular carcinoma, not just in these children and adolescents, but this effect already reached young adults, 20 to 27 years old. This figure illustrates the priorities and timetables of the Taiwan hepatitis B immunization program. And we can see that the program was launched in July 1984. And during the first 2 years, the vaccination only targeted the newborn of surface antigen carrier mothers, that is the high-risk infants only. And after July 1984 up to now, universal vaccination covering all the neonates was started. And during this period, plasma vaccine was used. And since October 1992, recombinant vaccine replaced plasma vaccine to be the vaccine we use in this program. So we studied the effect of the vaccination program to prevent liver cancer, and if we use the 1984 to 1986, the earliest 2 years as the relative risk as one for developing liver cancer, we can find that those born 86 to 1992, the risk ratio reduced, relative risk reduced to 0.57, and from 1992 to 2006, the relative risk further reduced to 0.24, suggesting a better cancer prevention effect in the later birth cohort. And we also analyzed the main risk factor for HCC prevention failure in 186 HCC patients born after the vaccination program. And we found that in comparison to those HCC patients with negative surface antigen mothers and who received 3 or more than 3 doses of vaccination, if we consider the odds ratio as 1, then the maternal surface antigen positive and E antigen double positive mothers, the high-risk mothers, their children's liver cancer incidence risk increased to 25 to 64 fold, so very, very high. So this is, we understand, this is the highest risk group with hepatocellular carcinoma prevention failure. And we also look this group with unscreened surface antigen, because in most part of the world, the maternal surface antigen is not screened, only the vaccine is given. And we found that in those who receive less than 3 doses of vaccine, 26-fold of the risk of developing hepatocellular carcinoma, implicating the incomplete vaccination also contribute to the prevention failure. So in summary, the liver cancer prevention effect of universal hepatitis B immunization in Taiwan has been extended from children to young adults, and this is a novel, encouraging finding. The liver cancer prevention effect in the vaccinated birth cohort is better in those born up to 1992, better than those born 86 to 92, and even better than that born in 84 to 86, suggesting that different vaccination strategies make difference in cancer prevention effect. It may provide a reference for studying strategies for other countries and also for other cancer preventive vaccines. HPV breakthrough infection by highly infectious mothers and poor immunization compliance are the 2 most important causes of liver cancer prevention failure. In spite of great success, still there are problems we need to overcome, because there are breakthrough, or we say vaccine failure. And the main causes of breakthrough HPV infection after complete immunoprophylaxis includes the most important maternal factor, high maternal viral load in E antigen and surface antigen positive mothers, and intrauterine infection. The second, the virus may develop surface gene escape mutant after immunization. And thirdly, the host factor, genetic hyporesponsiveness and immune-compromised host. So we studied 583 children of the E antigen and surface antigen double positive mothers. In spite of complete immunoprophylaxis with vaccine and HBIG, still there are 9 to 10%, 9.26% vaccine failure. In contrast, those second high-risk group with maternal E antigen negative but surface antigen positive carrier mothers, among 1,050 children, only 0.29% without HBIG, which is the strategy of our country. And if the mother self-paid HBIG at birth, then 0.14% become chronic carrier. So much lower than this almost 10% chronic carrier rate, the vaccine failure rate. So we then understand this group is the main group we need to work further. We then conduct prospective study to study the maternal viral load, HPV viral load, during pregnancy. And we can find that among those highest mothers, their viral load is more than 6 log 10 copies per ml during pregnancy. In contrast, those second high-risk mothers, the HPV viral load only 0.5% of the maternal viral load are above 6 log 10 copies per ml. Very much different. And the right side panel's figure shows horizontal axis, the maternal viral load during pregnancy. And vertical axis shows the outcome of their children, surface antigen positive rate. And we can find that those children with maternal viral load during pregnancy greater than 10 to the 7th to 10 to the 8th would have a significant risk of developing chronic HPV infection in spite of complete immunoprophylaxis. So, how to overcome mother-to-infant transmission? We should increase implementation of hepatitis B virus birth dose worldwide, as recommended by WHO. And we should give hepatitis B immunoglobulin immediately, as early as possible after birth. And we can consider antiviral therapy in high-risk pregnant women during the last trimester if this therapy is effective and safe. So we just recently report our result of a clinical trial. We screened the maternal HPV DNA during pregnancy, and those with greater than 7.5 log 10 IU per ml enrolled in this study under their consent. And we treat those mothers starting from pregnancy 30 to 32 weeks until 4 weeks after delivery. And in the control group, no treatment. And found that those control group, the viral load in these mothers are stationary. But in the treatment group, the viral load declined from 8 to 4 log 10 IU per ml, suggesting a significant reduction. And the outcome of their children, the HPV DNA positive rate at birth in control group 31.5%. In the treatment group dropped to 6.15%. And the HBsAg positive rate at 6 months old, this is the outcome. The control group 10.7%, and the treatment group 1.5%, significantly reduced. So, to fight hepatitis B and the liver cancer, we should block maternal transmission starting from fetal and neonatal period. And then we move to the second part, the carcinogenic role of RBNY in liver cancer. From our epidemiological study, we can find that a remarkable male predominance of liver cancer in all the ages. And very interestingly, the young children 6 to 9 years old have the highest male to female ratio, reached to 5 or 3. This is higher than other ages. So we start to think that these children very young have very low levels of androgen effect. So maybe there is a possible role of the Y chromosome encoded oncogene in the oncogenesis of liver cancer in this male patient. Since we have the liver tissues and the samples, so we study the HPV integration in our children hepatocellular carcinomas, integration into host genome, and we found that 67% of the HPV integrate into tumor liver tissues of HCC children, and 22% in the flanking tumor liver tissues of these HCC children, but 0% in chronic hepatitis B children's tissue without hepatocellular carcinoma. We further investigate the HBV integration site, the flanking sequence by inverse PCR, and we found human RBNY gene is the flanking sequence of HBV integrated site in childhood hepatocellular carcinoma patient tissue. RBNY is an RNA binding motif gene on Y chromosome. It is a male germ cell specific splicing factor. It belongs to the HNRPG family, and it is a testis-specific protein binding RNA through its RNA recognition motif, as shown here. This RBNY protein in the N-terminal, the RRM domain, and in the C-terminal domain, it contains 4 SRGY box, which is a protein interacting domain. And using our human male liver cancer tissue, we found that RBNY messenger RNA is specifically expressed in around 1/3 of our male human hepatocellular carcinoma tissues. Here in our childhood hepatocellular carcinoma, 38%, and in adult HBV, HCV, or non-B, non-C HCC tissues, 31 to 44%. And very interestingly, in the fetal type hepatoblastoma, 67% can find RBNY and messenger RNA expression. However, in other cancers, such as colon cancer, renal, lung, stomach, and prostate cancer, 0% RBNY expression. And RBNY is expressed normally in the testis tissue, but not in other tissues. So we ask, can RBNY regulate cell proliferation, stemness, migration, and/or invasion? Is the expression of RBNY in human liver tissues associated with the clinical outcome of HCC patient? Which mechanistic pathway is used by RBNY to exert hepatic oncogenic function? Our results reveal that RBNY promote colony formation in rodent fibroblasts and cause tumor formation, as shown here. This is tumor, and this is tumor. In nude mice, and this is the control. RBNY knockdown in HepG2 cells result in reduction of chronogenic growth in soft agar. And very importantly, RBNY specifically expression, liver-specific expression, can lead to precancer lesion, as shown here, adenoma, as shown here, and hepatocellular carcinoma, as shown here, in transgenic mice. And it can enhance chemical carcinogen, DEN-induced carcinogenesis. We found that RBNY expression in Q7 cells, this is the control, and this is the expression, can enhance the proliferation. Again, this effect also found in HepG2 cells. RBNY expression can enhance the sphere size and the sphere number in comparison to the control. And here it can show, in comparison to the control, the sphere numbers enhanced in RBNY expressed cells. And also in this figure we can find the invasiveness. RBNY can enhance the invasiveness in Q7 cells and in Hep3B cells. And also we found that RBNY expression can enhance the migration, as shown in the right side panel figure, in comparison to the control. And this is the migration distance. RBNY can enhance the migration distance, as shown in this figure. And very importantly, in human tissue, in HCC patient, if the RBNY is positive, found expressed in the liver tissue of this patient, the survival rate is much lower in comparison to those patients of hepatocellular carcinoma with negative RBM1 expression. In order to study the stemness characteristic of RBM1, so we collect fetal liver tissues in human under parental consent. And this is the female fetal liver tissue. We found negative expression of RBM1. But these three are male fetus liver tissues showing positive expression of RBM1 in the hepatoblast shown here, and also in the cholangiocyte as shown here in the bile duct. And this right side panel figure shows RBM1 in red color stand in the cytosol of these cells. And it is colocalized with the markers albumin and alpha-fetoprotein. These two are the hepatoblast markers. So we can say that RBM1 is expressed in the hepatoblast. And CK19 is a marker of cholangioblast and also a stem cell marker. And we can find that RBM1 expression colocalized with CK19, suggesting it's expressed in the cholangioblast. And again, we can see that using RT-PCR to study the mRNA expression, we found that in those fetal male liver tissues, RBM1 mRNA expression is positive here, we can show here. But in the female fetus liver, no RBM1 expression of messenger RNA is found. And the lower panel shows the Western blotting. The protein expression, we can find that RBM1 protein expression is present in this male fetal liver, but is absent in these female fetal liver tissues. And very interestingly, after birth, RBM1 expression disappeared. Now, this is a 7-month-old infant liver. We cannot find RBM1 expression in the hepatocyte. Only very rarely we can find RBM1 expression in the bile duct cholangiocyte and also in the ductal plate. And this is adult 38 years old male. We cannot find RBM1 expression in the hepatocyte, and very scarcely we can only find a very low rate of adult tissues in the ductal plate expressing RBM1. And we further studied the expression in mouse fetal livers. We found that RBM1 expression is in the cytosol of the fetal hepatocyte. And this expression levels declined when the fetus is getting older. And RBM1 expression, and this is DAPI and DAPI stain and RBM1 stain. We can find that RBM1 no more expressed in the hepatocyte postnatally. Only scarcely we can find RBM1 in the cholangiocyte expression. And we further studied RBM1 and epichem expression pattern. We found that these two are the cancer stem cell markers of the liver. And we found that RBM1 can colocalize with CK19. And RBM1 expression can colocalize with epichem, suggesting this colocalization with cancer stem cells. And we further use magnetic microbeads to isolate epichem positive cells. And we found that those cells with plenty of epichem expressing here, RBM1 expression can be found in these cells. In contrast, those without epichem expression, the cells, we cannot find RBM1 expression. And we use immunocytochemical staining to stain RBM1 and epichem, and they often staining localized at the same site. And this is human liver cancer tissue. And another liver cancer tissue, we also find a similar result. The epichem expression and RBM1 expression are localized as the arrow and arrowhead shows at the same location, and also in the cholangiocyte. So we think that RBNY is a novel onco-fetal protein. And in order to study the mechanistic pathway, we use human protein microarray, and we found that GSK3 beta is one of the candidate protein binding with RBNY. And using this GST pull down, we can find that RBNY can pull down GSK3 beta. And using the co-IP study, we can find that the HA GSK3 beta can pull down RBNY. And using confocal immunofluorescence study using Q7 cells. And this column illustrates the RBNY staining, and the second column illustrates GSK3 beta staining. And we can find in different cells, we can find the co-localization of RBNY and GSK3 beta in these studies. So we now understand that RBNY can bind GSK3 beta. We further demonstrate that after binding, RBNY can catalyze GSK3 beta's phosphorylation and inactivate GSK3 beta's activity. This cartoon shows GSK3 beta. It can bind its substrate at the serum 9 residue site. And if this S9 residue is phosphorylated, then GSK3 beta's function is inactivated, and GSK3 beta lost the substrate binding activities. These left side panels using IP kinase assay showing that with the presence of ATP, GFK-RBNY, HA-RBNY, and endogenous RBNY can phosphorylate GSK3 beta at S9 residue and inactivate GSK3 beta. And this lower panel figure shows using GSK3 beta specific Z-lite kinase assay, we demonstrate that when GSK3 beta bind with RBNY, and GSK3 beta lost its substrate binding activity and lost its phosphorylation activities. So we understand that RBNY can bind GSK3 beta and inactivate GSK3 beta, and then can disrupt the beta-catenin destruction complex, resulting in beta-catenin stabilization and accumulation. From these two co-IP studies, we found that without RBNY, then this complex with GSK3 beta and AXIN and APC and beta-catenin can bind together. But in the presence of RBNY expression, then lost this complex, they cannot bind together. So beta-catenin is stabilized. Again, in this figure, we can see that with the presence of RBNY, then GSK3 beta cannot bind APC or AXIN. GSK3 beta can only bind RBNY. And this right side panel shows that, again, in the presence of RBNY, we can see plenty of beta-catenin and its downstream molecules such as cyclin D1, c-MYC, glutamate, synthetase, etc. But when we inhibit RBNY with siRBNY, then this function gets lost, and no more beta-catenin and its downstream effectors present here. And we further found that with the presence of RBNY in Q7 cells, HepG2 cells, and SK-HEP1 cells, we can find that, again, we can find that the presence of plenty of beta-catenin and GSK3 beta levels. However, with the NES mutant, the RBNY NES mutant, which restrict RBNY in the nucleus but not in the cytosol, then the RBNY's function of restoring beta-catenin is lost. And Furthermore, we can see that with the presence of RBMY, the nuclear beta-catenin level is increased in HU7 cells and HepG2 cells. So we further use the spheroid assay to study the cytosolic RBMY's role in mediating hepatic sphere growth, that is the self-renewal ability. In the upper panel, this figure shows red color RBMY staining and green color. The green color shows that GSK3 beta, which is colocalized in the cytosol of these sphere cells. And the lower panel shows that the red color RBMY and beta-catenin shows in green color, and beta-catenin is localized at the periphery of these spheres and is then in the cell's nucleus. And using HA and HA RBMY stable cell lines, we demonstrate the sphere growth. And we found that with the presence of RBMY, the sphere number is enhanced. And in the presence of Wnt 3A and RBMY, it further increased the sphere numbers, suggesting their collaborative role of enhancing sphere growth. However, still in the presence of RBMY, if we knock down the GSK3 beta or beta-catenin, then the RBMY's role is absent, suggesting that this RBMY's role of enhancing sphere growth is mediated by the GSK3 beta and the beta-catenin. And also shown in this figure, we found that RBMY can enhance the sphere growth. But if we use RBMY NES mutant to restrict RBMY in the nucleus, then it lost its function to enhance the sphere growth, suggesting that the cytosolic RBMY is very important in enhancing the sphere growth. We further analyzed the secondary spheres, and we found that, again, those with wild-type RBMY, the beta-catenin level is high, and also the downstream c-MYC, epicam, and other molecules downstream to beta-catenin. However, if we use NES mutant to restrict RBMY in the nucleus, then this function disappears, no more accumulation of this beta-catenin and its downstream molecules. And we use nude mice xenograft assays to demonstrate the tumor growth. And we found that with wild-type RBMY, the tumor growth volume is high. But if we use RBMY NES mutant to restrict RBMY in the nucleus, then the tumor volume is very small, or even without tumor. We further looked at the correlation of this RBMY expression pattern with our patient, hepatocellular carcinoma patient. And the left side panel figure shows the normal testis, showing that RBMY is expressed only in the nucleus of testis cells. And these four figures illustrate different expression patterns of RBMY in human cancer, liver cancer tissues. And this is the negative RBMY expression pattern. And this is the RBMY nuclear expression pattern. And this is the RBMY nuclear plus cytosolic expression pattern. And this is the cytosolic expression pattern. And in the lower panel, we use black bar to demonstrate RBMY cytosolic pattern, and use this green bar to illustrate nuclear and cytosolic pattern. And we can find that RBMY cytosolic expression pattern is correlated with the liver cancer BCLC staging advanced cancer, B and C stage, and also correlate with the bigger tumor size greater than 5 centimeters in size. And also it correlates with the early recurrence in this patient, and also the metastasis, the presence of metastasis. And very importantly, our 205 HCC patients, we found that the RBNY expression pattern, if it's cytosolic expression pattern, the 5-year survival rate is the worst. And the nuclear and cytosolic expression pattern, the intermediate. And those express RBNY in the nucleus or negative RBNY expression, the higher survival rate. We also investigate the microRNA interacting with RBNY by using microRNA array. And these more details will be presented in the poster session. And we found that the RNA levels are RBNY. Here, the horizontal axis is RBNY expression level. And the vertical axis is the miR34A. We found that RBNY messenger RNA level is negatively correlated with miR34A. And also the downstream molecules of miR34A, such as here, BCL2, CD44, and SNAIL, and ZEB1. So in summary, by establishing an interaction with GSK3 beta, RBNY can bind GSK3 beta, and it participates in the Wnt pathway by attenuating the GSK3 beta activity and accumulating nuclear transport into the nucleus beta-catenin, and thereby trigger tumorigenesis and enhance the stemness, the migration, the S-phase entry, the proliferation, and very importantly, correlate with the poor survival of our HCC patients. Continuous efforts are needed in the future to study whether the liver cancer preventive effect of infantile hepatitis B immunization can be extended to older ages who have higher HCC incidence than with waning immunity after hepatitis B immunization. And how to successfully break mother-to-infant transmission of HBV to improve the effect of liver cancer prevention is also very important. Since RBNY expression is absent from the normal human tissues except testes, so we think that RBNY may represent a feasible therapeutic target for the selective eradication of HCC cells in male patients. So we need to work further. I would like to thank our liver cancer epidemiologic study group, particularly Professor Chen Jianren and Dr. Liu Sanlin, Fan Liqin, Ying Jingyang, Eva Liang, and Jasmine Pu, and very important, Taiwan Hepatoma Study Group in the hospital, major hospitals in the whole Taiwan, and also the Ministry of Health and Well Health, Health Promotion Administration, and Taiwan Cancer for Disease Control. And for the oncogenic role of RBNY, I would like to thank particularly Dr. Cai Huihui and Dao Zhengcui. They conduct most of this work. And Professor Li Bohuang, Zheng Yongming, Su Dexuan, Gao Peiqi, Jia Feng, Li Jiannan, and Professor Xu Huiji. And I would like to take this precious opportunity to thank NHI for the grant support in the long time, and the reviewers' comments are very helpful to our research direction for liver cancer. Thank you very much to your kind attention.